Thank you, Cindy. My name is Nicole Wolter. I am part of the complex team here at the San Diego Supercomputing Center, and you all are here to learn a little bit more about Bash shell scripting. This presentation, so the slides and any of the slides that the complex team presents in these webinars or at the two-day workshops can be found at the bit.ly link there. Someone asked a question about if this was hands-on. If you happen to have a Unix system or a Linux system, you can do a clone from this GitHub repository that we have listed here, and all the examples that I'll be going through are in that repository, and you can follow along with me. Again, if you don't want to follow along, or if you don't have a Linux system right now, you can pull these at any time later on. So just very quickly about Complex. Complex is a NSF training program. We're in our third year now, and we're specifically kind of looking to help users who aren't the traditional, computer scientists. So people who aren't developing their own codes kind of get the skills they need to run on HPC systems at SDSC, or not SDSC, but in the access environment in general, or any HPC system. They're generic talks. I apologize. Today we are going to talk about shell scripting. I'll give a brief overview of it. So shell scripts are just programs that are executed by a Linux shell. It's just a file that contains a sequence of commands that are executed by the shell. It's going to execute them line by line. It'll allow you to perform any action that you can do on a command line. It will let you do things like navigate to directories, create folders, launch processes. Again, anything you can do on the command line, you can do in a shell script. It allows you to automate repetitive tasks. They're really good for system administration, software deployment, data processing, and task scheduling. They're really versatile, so they're capable in handling file manipulation, database monitoring, text printing. It also has the ability to do conditional operations. You can do looping. Again, anything you can do on the command line, you can do in a shell script. Sorry, something popped up on my screen there. So in general, just a general comment, when do you use shell scripts and when should you use a more complex programming language? If it's going to be short, like less than 100 lines, even 100 lines seems a bit long for me, but if it's less than 100 lines and you have really straightforward logic, then a shell script is definitely a great way to go. Pretty much shell scripting is a hack to achieve something you need to do kind of quick. So shell scripts are really portable and they're easy to write. You don't need to learn any new languages for it. However, they are simple, but that kind of makes them simplistic, which makes them not real well suited for large complex tasks. They don't support complex data structures. There are some challenges in error handling. And while it can do some database stuff, it's not well suited for database tasks on like a high level. It is an interpreted language. So with compiled programs, you can fine-tune your code to take advantage of specific architectures. Again, since this is interpreted, it's not compiled, your performance is going to be is going to take a hit for that, or not a hit, but it's not going to be optimal. So again, so if you're doing really robust calculations, shell scripts are generally not what it is, not what you want to use. The other thing is shell scripts tend to be written kind of, as I mentioned, as hacks. So the quality of shell scripts is normally not that good. Generally, people start and do something, and after the motto, if it ain't broke, don't fix it. But if it works well, you hand it on to other people in your lab, and lots of people use it, but it's not necessarily documented. And so generally, again, it's harder to maintain these than more formal codes. The final thing, kind of drawback from it, is that it is very sensitive. So the rules are very specific, the syntax is very specific, and we'll go into that in the next couple slides as we go along. So we specifically said that we're going to talk about the Bash shell scripting today. And so just a little bit of why we chose Bash. As you may all be aware, if you have a Linux system, there are lots of shells already on there for you, and they're in various locations. And there's Bash, there's SH, there's CSH, there's KSH, there's ZSH. The reason we chose Bash and the reason we like Bash is because most of the HPC systems use Bash as its default, so that's simple for everyone. But in addition, Bash has a lot of really good features. So it allows you to do command history. So it allows you to keep a record of all the commands you've done in the past, and you can easily recall them and re-execute them. It also gives you a lot of job controls, so you can run multiple commands at once. You can run them in the background. You can manage them by suspending them, resuming them, or terminating them. And what we're talking about today and what's really good is it has a really robust scripting syntax. It has a bunch of features. It allows you to use aliases. It allows you to use arrays. It allows you to do brace expansion, pattern matching, and conditional expressions. So it's a very robust shell in that sense and allows you a lot of flexibility. So the rest of this presentation is following a Bash scripting style guide that's available at this Google GitHub location. So it's really important to write good code, even if it's just a shell script. So we want to follow these conventions to make sure we promote good readability of scripts, that they're able to be maintainable, and that they're portable. A couple things kind of in the forefront that we want to talk about is that generally, when people write shell scripts, they end it with the file extension of .sh. You don't need to have any file extension at all, but again, when you're coming back to it and you have 50 files in a directory, it's nice to be able to easily distinguish what a file is for. We strongly encourage you to use comments to document your code. Important thing is indentation should be 2 spaces. You should definitely not use tabs. Again, a style thing is to leave spaces between the blocks for good readability. And then I think, yeah, if you inherit somebody else's code, you should kind of stay faithful to the existing indentation. So that's the only caveat of when you might not use the 2 spaces, but you should just use the 2 spaces. So just reiterating what I said before, shell scripts can be as simple as a list of Linux commands. They are plain text files. They contain commands. They contain comments. The first line is always going to define the shell that you're going to be used, and it's going to be followed by a series of Linux commands and comments. A note that all lines that start with a hash are considered comments by the interpreter, and so they will not be executed by the interpreter, but just because it's not executed doesn't mean that the interpreter doesn't do something with it. So it's not necessarily ignored. Going forward, the way we're going to present our examples is all of our code is going to be presented in a gray box. As we introduce new things, we're going to bold those. All are how to run them, and the results are going to be presented in a blue box. Note the $sign in the blue box, so that $sign in Bash is a special character, but it is also the command prompt in Bash. So when you see the command prompt, it's going to indicate that's the command that we're running. If there's no command prompt, it's going to be the results that are coming from running that command. I'm going to start with a really simple example that you get with when you learn to code anything new. So we'll start with the hello world. The first line will always be the shebang, or what we call a shebang, and that's going to instruct the operating system which interpreter to use. Basically, an interpreter is just a program that tells the that's going to execute the commands from a higher level language directly instead of having to compile it into machine code. So there are two different ways that we can indicate which shell or which shell we are going to use. As I mentioned before, there's lots of shells that are installed with many Linux systems, and there are various versions on the Linux system itself. So you can have bash located in many different areas. If you use the hard code the path or direct path, so the first one bin bash, this is where it's usually located, but sometimes it's not. So in case you're porting this code to other places, by hard coding it, you make it a little less portable in case that bash is in a different location. The other option you have is to use your environment. So the hash not user bin environment basically goes to your environment variables and finds the first instance of bash that's installed there. This makes it more portable because any system you're on, it's going to find something. But in case you're very specific into which bash you're using, it could cause some security problems. Note about comments. Comments, as I mentioned, always start with a hash. Everything past that hash will be a comment. So you can't add any commands after that anymore on the line. You have to put it onto a new line. And then for this particular script, we're going to use the echo, which is just going to print hello world. So to run this command, the command prompt will do a // and the hello world.sh because this is an executable. We can run it directly. And then what's going to return to standard out is hello world. The echo command by default adds a new line character, which means it'll just give you an extra line there. So if for some reason you want to concatenate various echoes on the same line, you can use a -n, and this is going to suppress the printing the new line. So in this case, we just echo hello, but we use a -n, so we know that the next thing that the echo world is going to come on the same line as the hello. So in shell scripts, special comments are lines that start with the hash, but they're going to serve some sort of purpose beyond just documentation. They're really important because they can influence how the script behaves, or it's going to provide some metadata, or it's going to be interpreted by some other tool or the systems that's going to modify the behavior in some way. So we already talked about the shebang. The other one that if you continue with the system or you're using HPC systems, or if you have already used HPC systems, you're probably familiar with batch scripts, so batch scripts, and they're basically just are schedulers. Batch scripts are just shell scripts. And in them, you'll be able to do anything you can do in these, but at the beginning of all the batch scripts, they have these directives. So it's the hash, the sbatch or hash for PBS. And those are going to be used by the scheduler itself to configure the job submissions and instruct the scheduler how to schedule a job. So it can tell you how long the job should run, which queue to use, stuff like that. The other two I put in here, just so that's note that there's other comments you can have. You can put in editor hints. So for Vim specifically, this example, it can give hints to the text editor. This specifically tells you how many spaces you want a tab to be. There's also a shell check directive. And basically shell check is just it's like a spell check for a shell. And it's basically going to help you avoid subtle bugs and help you write cleaner, safer code. So with all things, the first thing we need to be able to do is to handle variables. Variables are going to let you store data. Then you can use those variables to read, access, or manipulate other data in your script. Variables can store numbers, characters, and strings, but it's important to note that there's no specific data types in Bash. So how those variables are going to be handled is going to depend on the operations you use on them and the syntax you use with them. There's some general conventions. Variable names can only have uppercase, lowercase, digits, numbers, and underscores, and they should always start with a letter or an underscore. They're super case sensitive. I guess super, it doesn't matter. They're just case sensitive. if you have Bob with a lowercase and Bob with an uppercase, they are two very distinct variables. Important to note, spaces are not allowed. Spaces are, again, Bash is very, very sensitive, so spaces are used for many other things, and spaces have lots of meaning. Blank spaces have meaning. There are predefined words in Bash. So there's like, there's if, there's else, and all those predefined words cannot be used as variable names. Other thing to note about variables is that in general, all the variables in Bash are global variables, but you should take into consideration scopes. So depending on if you're in a shell or in a subshell, we'll discuss this, like the specifics about this a little bit later. But also there is the ability that within a shell script that you can define local variables, but they have to be defined separately. So variables can be characters, digits, numbers, or strings. In a Bash script, when you quote a string, it's going to set it apart and protect its literal meaning. So with the quotes, it has the effect that it protects all special characters in the string, so it doesn't get expanded or reinterpreted. So in this first example, you can define variables using the equal sign, and then you're going to be able to access those variables by preceding it with the dollar sign. So in this first example, we are going to first define our interpreter with the hash bin bash. Then we're going to put in a comment because we like to write good code, and this is basically our intro to variables. Then we're going to assign two shell variables. The first is going to be equal to Bob, and then last is equal to Smith. Variables can be redefined at any time. So if we put another line right after this last and said first equals Bob1, then when we did the echo below, it would be Bob1, not Bob. So again, we run it with the dot slash, and then it prints out our first name is Bob and our last name is Smith. So we have a couple of best practices with variables. And one of the things we want to have is to make them disambiguous. So by enclosing the variable name in curly braces before accessing the value, you ensure that the name, so what you have within the curly brackets is not misconstrued and it's easier to read. So using the curly brackets distinguishes between the variable name followed by the string last and the variable name last, for example. So in this is very similar to what we had before. We have Bob and Smith, and we're going to echo Bob, and then we're going to echo Smith. So to be even more particular, again, this is a little bit overkill, especially for this very simple example we have here. But because Bash is so sensitive and with spacing and special characters, to make it super defined, to make sure that there's no disambiguation, make sure that we have everything we want in there, we can add quotes to this as well. So in this example, it's Bob and Smith, and we're going to put our string that we want printed in quotes, and we're going to put the variable in quotes as well as curly braces. And it essentially does the same thing, but it does it in a more secure fashion. So we've been executing the shell scripts before, so let's take a moment to discuss this a little further. So there's three ways of executing shell scripts. There's a standard way, which we have been doing up until now. And so what we have to do for the executables, we have to make it an executable. So we have to use the chmod command to change the file permissions itself to ensure that it's executable. Once we make it executable, then we can run it directly as a command. Note that when we do the standard way, we are running it as a new subshell. The second way we can do it is the explicit way. basically calling the shell itself. So if for some reason you don't want to change permissions on a file, or you can pass the script as an argument to the shell interpreter itself. So by using bash, we know that we're going to be using bash. The interpreter is bash and the script.sh. When we run this way, we are also creating a new subshell. The other way we can do this is the source way of running it. When we run it as source, we are actually going to run it in the current shell. So, and this is important because you are going to actually modify your current shell. So let me give an example of why that's important. So our script is very simple. All we're going to do is assign a string ABCD. So when we do the standard way and create a subshell, it means that everything that's run in the shell is in the subshell is going to stay in the subshell and won't bleed out back into your parent shell. So if we run the exec.sh, it will assign the variable in the subshell, but when it's finished and you come out into your normal and you echo my string, it's not going to know what it is. However, if you do want your environment to change, you can say the source exec.sh, and then your whole environment changes. So now for the rest of your session, unless you change the variable name, you can echo my string and it will give you back ABCD. So shell scripts can accept command line arguments, which is very useful. The command line arguments are you can recall them with the $123, basically storing the first command that you put in as the first, the second, the third, what have you. Notice that there's not a $0 here. The $0 here is special. The $0 will indicate the name of the shell script you are in. Kind of as a side thing, if you're on the command prompt, if you just type echo $0, it will actually give you the shell that you're currently in. So in this case, we want to know which script we're in. So we're going to echo greetings from $0, which will give us the script name. And then when we do the // we're going to put, we can just do space, excuse me. So there's a couple ways that we can provide these. So we just put each variable or each parameter delimited by a space afterwards. So in this case, we do the position.sh and Bob and Cal, and then we echo where we're coming from. So we echo that the name of our script is posh.sh. Then we hello Ann, Bob, and Cal. So the way we did it using these using 1, 2, 3, we can hard code it, but we can make it more flexible. So the positional parameters gives us some other special characters that allow us to interpret some stuff and to make it more versatile. So the special ones, so there's the $hash, which is going to return the number of arguments that were submitted. So we could submit 1, we could submit 100, and this is just going to tell us how many it is. The $star, the star is a wildcard, and it's pretty much sending return all the variables that were presented, and it's going to put it in as a single string. And the $@ is going to be an array of arguments as separate strings. So we can echo the number of command line arguments. If we do posh and Bob and Cal, we have 3 arguments. So our first is a repeat, greetings from the script we're writing. We have 3 command line arguments, and the command line argument, if we do it $, we're getting all 3 of them as a single string, and in the second one, we get it as an array of single strings. Another great feature of Bash is that we can do looping and branching. The loop, we have 3 different types of looping that we can do. We can use for, while, and until. Basically, looping just allows you to reuse a block of code by enabling the repeated execution of the blocks using constructs. For iterates over a sequence of items, while repeats as long as the condition is true, and until is going to repeat until the condition becomes true. We can also do branching, which is just a variation depending on your preference. And it's going to enable you to do conditional execution based on specific criteria using the statements. So the if is going to execute code conditionally. The case is going to provide you a multi-way branching based on pattern matching. So the first one, probably the most common loop that we have out there, is for loops. So a for loop is going to allow you to execute a statement a number of times. Loops let you iterate over items in a list. Lists can be defined in multiple ways, including white space separated set of items, wildcard expansion, or a range of numbers. You can also capture output from executing a command to put into this. So the way these for loops are going to work is it's going to use a for, and then it's going to provide a dummy variable. In our case, we're going to use var. And this is going to allow you to use that dummy variable inside your loop. Then it's going to be followed by an in and then the list. The list is going to be the collection of items that we're going to iterate over, and then a semicolon and a do. So best practice is for the do and the for to be in the same line. Then we're going to have all the commands that we want to be executed based on if you happen to be in that list. With all the branching and loops, you always need to find some way to conclude it so that it drops out of that. So it's not indefinite. And we will close the for loop with a done statement. So we can iterate over an explicit list of items. This isn't very flexible, so I'll show you later how to do this. But if we have exactly 3 items, we can explicitly state this, or we can explicitly state this if we have 100 items and we only want to print 3. This allows us to format how we're going to present this. So in this case, we're going to for name is going to be our dummy variable, and then we're going to provide a list, and the list is provided from the parameters when we submit the job. So in 1, 2, and 3, and then do, and then we're just going to print the name. So we'll do for 1 Bob, Susan, and Andy, and I will do hello Bob, hello Susan, hello Andy. Recall that we mentioned that spaces were important. So if you have a name that is multiple names together, you can't just say Billy, Bob, Susan, and Andy. You need to put quotes around it to ensure that it realizes that it is one name. So in addition to the quotes in the script itself, you need to put quotes around when you submit the parameter itself as well. So it provides a suggested exercise to get rid of the quotes around the 1, 2, and 3, and then see what happens in the second example. So let's look at that. So in the correct statement, we use the quotes around it, and so what it interprets it as is in for name in, and Billy Bob is in quotes, Susan is in quotes, and Andy is in quotes. So they're all in individual. And so then it will respond to you, hello Billy, Bob, Susan, and Andy. If you get rid of the quotes, then it doesn't know that Billy Bob is one name. So it's going to return hello Billy, hello Bob, and hello Susan. And again, because we only have the name, we explicitly asked for the first parameter, second parameter, and third parameter. We're not going to see Andy at all. But we can make it more versatile by using an array. By using the $@ it means it can take any number of parameters, and it can be flexible and it can change over time. So for name in our array, do something. So in this example, we're doing the exact same thing, but we're doing it in an array, so we don't have to explicitly state the 1, 2, 3. So hello Bob, Susan, and Andy is the same as it was before. And for hello Billy, Bob, Susan, and Andy is the same. Now, if we got rid of the quotes and we did this, then we would get hello Billy, hello Bob, hello Susan, and hello Andy. Up until now, we talked about the echo statement, and the echo, and that works just fine, but it's kind of notoriously inconsistent. So if you are planning on porting this code to other systems, you might want to be more specific with how you format your print statements. And so you can do that with the printf statement. So the printf statement is follows the C standards basically. So in this example, we're designating, well, we're not designating, we're naming things my string, my int, and my float to define what they are. My string is ABC, my int is 1, 2, 3, and my float is 4.567. And then we can printf, we can define what we're printing in there as well as the variables that we want to put in there. And with those variables, we can format how those variables are presented. So in this example, they are all strings. So we just put %s. Unlike echo, you have to explicitly state any new lines that you want to have in there. So the \n indicates that it's going to print string and then the variable and then return. So if we run this, we'll print the string ABC, 1, 2, 3, and 4.567. Now with printf, we have the ability to define more fine-tune. We can identify if it's a string, we can treat it as a digit, or we can treat it as a float. And we can also kind of define how many characters we want. So in this example, we want to make sure that we're only printing that the field is only going to be 8 characters long, and we're going to print a string, an integer, and a float. The %8s specifies that the string is going to be exactly 8 characters wide. The %8d is the integer is 8 characters wide, and the %8.2f specifies that it's going to be a float that's going to be 8 characters wide, but it's going to have exactly 2 decimal places. So let's look at the difference between what we did before with the echo and the print statement. So kind of the big difference is kind of your alignment. So when we define that we want exactly 8 characters, it's going to kind of right align things for us. So it's a little easier to see. It's also going to specifically concatenate or truncate, round to the decimal places that I specified. With the echo statement, it kind of right aligns and there's no concatenation. So the next thing we'll talk about is the if statement. The if statement is used to conditionally execute a block of code. The strings can be compared using equals, not equal, less than, greater than, less than equals to, or greater than equal to. For string comparisons, you'll use these square brackets. If it's an integer, you'll use these round brackets. Note that you can do string comparisons with integers in the square brackets, but the operators that you use on them will need to be different, because if they're in the square bracket, they're going to be done kind of, they're going to be evaluated as strings. So in this example, or the format that it uses is you have an if, then you have your test statement within the double square brackets, that it ends with the semicolon. The then and the if should be on the same line. Then you're going to have your series of commands, and the if statement is going to be concluded when you do the inverted if, so fi. The spaces before and after the square brackets and the square brackets and the rounded brackets are very important. They have to be there. So we'll look at string comparisons a little more closely. String comparisons are lexicographically first, which means it's going to be evaluated as it is in the dictionary. So if we, so ABC or A is going to be before AB is going to be before ABC. Similarly, 1 is going to be before 2, 1 is going to be before, but 1, 2 is going to be before 2, because again, in a dictionary, it's going to read from right from left, and the 1 is going to come before the 2. So if we just look at this example at kind of what we talked about before, we have 2 strings. In the first one, we have ABC and ABC. And when we go through, it's going to find that in this first one, they are equal. And so ABC equals ABC. Second one is ABC and DEF. It's not equal, so it's going to skip that one. It'll come down, and ABC is less than DEF. Similar when we do it in reverse, DEF is going to be greater than ABC. Then we'll do this string comparisons of numbers. So if we use 2 and 3, 2 is going to be less than 3, but 12 is going to be less than 3. So if we want to use, we can do this for integers. We can use those same operators on integers if we use them in the rounded brackets. So in this example, if we compare 1 and 1, 1 and 1 is going to be equal, 1 and 2, 1 is going to be less than 2, 2 is greater than 1, and 12, as we expect, will be greater than 1. So here's just kind of a little summary and a cheat sheet of what I went about. This is more for later reference, but in summary, the square brackets are going to be used for string comparisons, partial matches. The rounded brackets are going to be used for arithmetic and integers. The gotcha with the brackets is that the symbols that we're using, like less than, greater than, are going to be compared in alphabetical order, not numerical order. But to get around that, if we wanted to use strings, we can use the less than or greater than signs to compare that way. So we did the simple if statement, but if we want to get more complicated, we can use else if statements. So we can have as many else ifs as we want. We'll start with the if some test, then print whatever it is, and then have further options with the else if. The else if is going to follow the same format as the if statement. So else if, the test, semicolon, then. The else if, this allows, it allows you to kind of have a drop through with the else. So you can do if, else if, else if, else if, and if it doesn't use any of the other ones, you just want it to drop through and do some default action, then the else will allow you to do that last action. So in this is pretty much the same that we had before, but this time, instead of having to run through each one, it allows us to do a few fewer lines. So if we compare ABC and ABC, they're going to be equal. ABC is less than DEF, and DEF is going to be greater than ABC. So we can also do file and directory tests. Now, why would this be useful? Many times when we're writing code or we're checking for things, we want to know if a file is where it is. I work in the user support group here at SDSC, and very often we'll get tickets of, why is my thing not running? It says my file doesn't exist. Well, your file doesn't exist, but what you could do is in your script, you could put in the script, does the file exist? If it doesn't exist, it should abort immediately and give you an error. So the things we can check for, we can check what type of file you have. So you can check for regular files, you can check for directories, you can check for symlinks. It can check if, again, if it's a file directory, then we know it exists. But if you didn't want to check those things, you can just check if the file exists. We can also check what permissions it has. A lot of times when you need to, if you want to run other scripts or other processes within, you need to make sure that they are executable. So you can check first if you can read them. So if it's an input file, it needs to be able to be written or read. If it's an output file, you need to be able to write to it. So by using the -R, the W-X, you can see what file permissions are on them. Note when you run the script, these file permissions are going to be based on who you are running the script. The last thing is we can check if if it's an empty file. So sometimes when we do output, if something goes wrong, you can tell if something went wrong because your output file is empty. And so this is a quick way to check that. Here are just the examples. If you did download or if you cloned the Git repository, all these examples are in there, so you can check. If it's a regular file, by definition, it exists. I could have I should have maybe provided a list of what these files look like and the permissions they have. But you can see that all these different directories, it just checks what they are and what their permissions are. Another useful thing is a case statement. So case statements are going to be used to compare a given value against a list of patterns and execute a block of code based on the first pattern that it matches. The bash case statement is generally going to be used to simplify really complex conditionals, where you're going to have a lot of choices. So how this is going to work is the case statement is going to initiate the statement. It's going to be followed by some sort of expression to be evaluated, and that's going to be followed by the keyword in. Then you can have any number of patterns that are followed by that the rounded bracket. And each of those is going to represent a potential match for the expression value. And then after that is going to be all the commands that you're going to want to execute if the corresponding pattern does match. Each of those will be ended with a double semicolon. So it's going to terminate the command list for that specific case. And then you're going to also be able to have like this kind of fall through. So the star round bracket is going to act as the default case. So pretty much execute whatever comes after this if no other pattern matches. Similar to the if statement, the case statement is going to be cleared that it's at the end when you have case inverted, so ESAC. Other thing to note is that you can use multiple patterns separated by the or the pipe operator, but that list of operators has to be terminated by a rounded bracket. So, for example, in this example, we're just going to check what languages are for a country. So we see that we can use case, and the first we're going to read in a country. And if it happens to be Lithuania, then we're going to print Lithuanian. And because it's a printf, we have to be explicit and use the \n for the return carriage. There are more places that speak Romanian, so this gives us an example of that we can use our or our pipe option. So Romania or Moldova will print Romanian, and then similarly, Italy, San Marino, Switzerland speak Italian. Because we're in light of brevity for this, we didn't want to list all the options there were, so we used the catch-all with the star and the bracket, and so anything else we don't know what it is. So we can see over here for Italy, the official language of Italy is going to be Italian, Moldova's Romanian, San Marino, and again, we had to use double quotes around San Marino because it has two words and a space in there, or else it would have thought of the first as San versus, well, first would be San and the second would be Marino, and it would print unknown for those. So integer math. Integer math, as we mentioned with the strings and the cases, it can be interpreted by those double rounded brackets. So the syntax to do integer math is going to be the $, and then the equation is going to be within the double rounded brackets. There are the option of 6 operators. You can do sum, subtraction, multiplication, division, square root, and mod. Thing to note is that Bash by default only handles integer math. So it can't handle floats. So if in our example here, we do this for 5 and 2, the sum is going to be 7. The difference is going to be 3. When we divide it, it will be 2. 5 divided by 2 is not 2, but it will truncate it. Notice that it's not being rounded, but it's being truncated. However, we can handle floating point math. Since Bash only performs integer arithmetic, you're going to have to pipe your math into the basic BC, which stands for basic calculator, and that's going to be able allow you to handle decimals. The important thing is that you need to include this scale variable, and it's going to tell BC how many digits to keep. So what it specifically does is it sets the position of the output to 5 decimal places. If you don't set scale, BC is going to default the scale to 0, which means it's going to act exactly like, continue to act like Bash does, and it's going to truncate everything. So in this example, we use scale, we do what we did before with our addition, and then we're going to use this here string to redirect the command we did into the basic calculator. So our output is we're going to get the addition, we're going to see what our variables are, then we're going to print out the sum, the difference, then we're going to print out division and modification, the square root, and we can see that all down here. So in general, Bash scripting is very generous, or it's forgiving. Maybe forgiving is the right word. If it sees something that it doesn't understand or doesn't like, it's just going to ignore it and continue on. So to help with debugging and to make it a little more robust so that and help you out a little bit to fix things, you can set this EUO pipe fail command at the top of your script. So what the E is going to do is it's going to tell the script to immediately exit if it registers that there is specifically an error. The U command is going to treat unset variables to error, because by default it's not going to see that as an error. It's just going to ignore it. So this specifically says if I don't have this variable set, then it's an error, and the E is going to say I need to exit immediately. And Dash O pipeline propagates the errors in pipelines, and it's going to give you actually the response for that first error. So in this example, we set the pipe fail, and we are going to loop through the name like we did in the past. So we're going to use the dummy variable var for the list in that array, and then we're going to echo the name, the hello and the name. So if you'll notice that var and name are not the same. So if you ran this without the set EUO pipe fail line, it is just going to echo hello for you. But because you use the E and the U, it's going to say, name does not equal var, so name is undefined. And I've been told that that's an error, so it's going to abort for you and give you some reasons. Another really useful thing is that you can capture command output. So we actually saw this in an example, I think, above, where we did this with the BC command, the basic calculator command. We captured the command in there and we directed it. Here we can do this, but in this example, we're going to do it for dates. The syntax is going to be $ in single quotes, and it's going to be assigned to the variable. In theory, you can use backticks, but it's a little harder to read, and so we recommend using the $ in this round brackets. I apologize. So this we set it to the current date, we set it to the current time, and then we just echo what that is. Pretty straightforward. So up until now, we've given you a lot of things that can help you get started, and you can do quite a bit with what you have. But scripting, there's a lot more that you can do. But in in light of the time we have today, we're not going to be able to go all of it. So we just wanted to give you kind of teasers for some other stuff that you have out there, and also note that the other stuff that some of the other things we have here can actually you can learn more about them in other complex webinars. So the other important Bash features that are really important and useful, but we're not going to have time to go in today, are input-output. So I'll just mention redirection and talk about the read statements. There's other looping constructs that we didn't talk about today. There are substring tests that you can use and regular expressions. So input-output is huge. A script can take in one or more inputs, it can produce 0 or more outputs, and it can produce errors. So as we saw before, the script can take input directly from your terminal, or it can be redirected to a new file. You can append it to an existing file. You can also read in from a file. So this is just gives you some examples of what is available done, but let me kind of step back. I guess that's a little bit out of order. So there's 3 types of files that we have. You have standard in, standard out, and standard error. Standard in is coming from your command line. Standard out is coming from command line. Standard error. I'm sorry, that is incorrect. I apologize. But basically, what is being read in, what is being read out, and if there's any errors, that's also being read out. So you can capture output from a file, command, program, script, or code block by sending it as input to another file, command, program, or script. And so we use these redirection commands. So the greater than symbol is going to redirect output to a file. It's going to create the file if it's not present, otherwise it's going to redirect it. So you have to be careful with that. On the flip side, you can use a double greater than, which is going to redirect the standard out to a file and create a file if it's not present, otherwise append to it, which you also have to be careful with depending on what you're doing. The multiple is part of that here document. We also use that in the BC command at the end, where it reads directly from a value into a variable. We can also use the pipe command, which allows you to do chaining commands. You take the standard out from one command and put it into the standard in from another command. The less than symbol redirects your standard input into a file, or from a file into your system. The ampersand greater than is going to redirect standard out and standard error to a file versus just standard out. So in our examples, we talked about we can redirect input from a file. In the examples that we did before, we provided parameters when we ran a script, but in some cases we want to do it more interactive and allow users to interact with our scripts and give it a command prompt. So we can do that using read statements. You can echo something that says enter a string and then read that string, but you can also do it in one line by using the -p, which basically says this is my prompt and this is the string that I'm going to have. There's also while and until loops that we didn't talk about. So while loops are going to let you continue while a condition is true. The until is going to continue until while the condition is true. Until is until the condition is true. So these two codes that we have here do the exact same thing. Things with while and until is you need to have some tests, and we need to have some increment, or else they're going to be run on loops. So we initiate our counter outside the loop. While count is less than 10, do something, increment, and keep looping until it's done. So in the example, while, do the while loop, and we're starting at 7. So the first time we go in, 7 is less than 10. So we're going to echo 7 and then increment to 8, go up, count 8 is less than 10. So we go through that same thing, increment to 9. 9 is still less than. When we get to 10, it's going to stop. So it's only going to print out 7, 8, and 9. In the until loop, it's the exact same thing. So we're going to start with 7 and the count is it's not equal to 10. So we're going to echo the count, and then we're going to go back up and check if it's equal to 8, which it's not, and so it's going to print 8, and 9 is also not going to be equal to 10. On the next one, when it's 10, it's going to fall through because it matches that test. So substring tests. So these check whether a string is going to contain a specific sequence of characters. And this is going to use globbing. So globbing in Bash is a way to use wildcard patterns to match file names or strings. This is a lot easier than regular expressions, and it's directly built into your shell. So it is useful to have. What this is going to, in this example of the if statement, we are going to check if the string is equal to star, which is a wildcard, so globbing. So anything with the string and anything before and anything after, then we're going to print that the string contains the substring. Similar on the prefix in this bottom, if we just use the star afterwards, it's going to say this prefix followed by anything, and the last one, anything followed by the suffix. So in the substring sh, a, b, c, d, e, f, c, d, a, b, and e, f, a, b, c, d, e, f is going to contain c, d, it's going to start with a, b, and it ends with e, f. Regular expressions are more robust, so you can do a lot more stuff with the regular expressions. You can use them in the tests using the equal twiddle operator. Generally, we recommend that these can be kind of simplified. If you really want to use complex regular expressions, you should probably use awk, set, or grep. We do have a presentation on with Linux text tools that would goes more in depth on these. I strongly recommend it because, again, regular expression, and we also have regular expressions talk, and both of these are it's an easy button for a lot of things. So in these two examples, I'm running out of time, so I'm gonna gloss through this because we're not gonna go in depth on it. But basically, know that you can use regular expressions in these. So I just want to put these all together for you real quick. So this is kind of still a dummy small script, and in this script we're going to sort empty and non-empty files. So the first thing I want to point out is on the blue side, we're going to list all the files that are in this current directory, so that are named out.star. So if you list all of them with the -L, it's going to tell you how the size of the file as well as the name of the file. So the first number there is the size of the file. So the 4 means that they have something in them, and the 0 means that they're empty files. So what the script wants to do is we just want to check and see if there's a file and if there's not a file. So kind of the things we're going to do is the first thing in the script, we can make directories. So we make the non-empty directory, and then we make the empty directory. And then we're going to test and see if anything's, if the directory is empty, then we're going to move it into the non-empty, or we're going to move it into the empty directory. So in this case, when we run this sort of script, we use the wildcard star. So again, just like the ls start out.star, we're listing all files. So our list is going to contain all the files that start with out. So it's going to run through it. It's going to move all the files to where they want to be. Since we're using the array, it can have any number of files that we want to in there. And then we're going to check if the file is not empty with the -S. If the file is larger than 0, then it's not going to be empty. It's going to move it into the non-empty. You should also note that the file names, they have these tick marks around them and not the tick marks, and it's going to include both of those in there. So kind of on a higher level, so everything we've done to now is kind of dummy scripts. This is actually something that we do here at the center. We provide HPC resources for people that are purchased by the NSF. But when we bring them onto the floor, we have to prove that they are working as they're expected to. And so to do that, we do a bunch of benchmarks on them to prove that every node on there is working and is working efficiently. So one of the ways we do this is by running the high performance LinPack benchmark. The high performance LinPack benchmark creates a file for every node that it runs on, and this is kind of an example of that file. It tells us the name of the file that it's on. It tells us how long the script ran and if it passed or failed. So this is important for two reasons. Passed or failed is we know that the logic that the system is actually doing what it's supposed to. The time is important because we know that it's performing at the rate it's supposed to. But there are hundreds of nodes on these systems, so it would be very painful to have to go into each individual file and see what node it was on, how fast it ran, and if it passed or not. So we can write a script that basically goes through all the hundreds of files and collects all this information for us. And so the 3 points of information that we're pulling out are the node name, the time, and the past. So really quick script is we're going to print out the node, the time, and how many times it passed or failed. So for the files in the array, when we run it, we're just doing it, all the output files are saved into the directory called HPL. So basically, if you run this within that, run it, it knows where to find the files. For all the files in there, check, pull out the node name. So again, these commands, the head command, if you're not familiar with it, basically just takes the first line, or it takes the first couple of lines by doing the -1. It takes exactly one line. And so we return the first line into node. Then we use an awk to search for this string. When we know that string, we know that the sixth column is going to have the time element in there. And so from the file, and so we're going to put that in time. And then NP is going to be the number passed. So we're basically just going to count how many times it passed and count how many times it failed and then print it out. So the output of this is really nice because we can see if it passed or it failed, and then we can see the timing on it. So in the one case where it failed in the third line there, it ran really fast, but it failed. So we're going to need to go back to that node and find out why it failed. On the other hand, that second line, the timing is a little higher. So we might want to go in there and see why it took so much longer than the rest of them. So finally, here's just a cheat sheet of everything we talked about. Here are some references for you. And now I'm going to open it up for questions.